Hi everybody, I'm the greatest living inventor, and today we are doing my invention, Ehrenfest Comet disc. I'll write it down. You see, it's a short invention, it's just one page. I hope it will be quick. Ehrenfest. This is named after Paul Ehrenfest. Comet. Disc. Okay, so this one came to me after I heard of Ehrenfest paradox. Okay, so Ehrenfest paradox, I will tell you in a moment what it means, but I want to explain something easier before. I think first you should look at a video by Up and Atom. It's a girl named Jade. It's not about the Ehrenfest paradox, but it will explain to you a certain effect of Einstein's relativity that you need to understand this. Okay, so first you should look at Up and Atom. And the video is, she's called Jade. And the video's name is Einstein's pole in the bound paradox. Okay, if you look at it in Wikipedia, if you look in Wikipedia, the same thing is called the ladder paradox. Or the barn, the pole in the barn, it's the same. Okay, so after you look at the video, you will understand that in general, also in special relativity, things shorten when you travel very fast. They don't look short, they actually get short in the direction that you move. Okay, if I move in that direction very, very fast, like in the speed of light, I cannot. But if I travel close to the speed of light, then my tummy and my back will get closer. I will get squeezed like that. I will look thinner. Okay, so if there is a pole or a ladder, and it moves towards here. very, very fast, like the speed of light, then it will be shorter. It will become, for example, like this. Okay, with the same 9, 1, 3, 4, 5, 6. Okay, with the same, it's the same ladder, but it becomes shorter. Okay, not smaller. It will be the same in this aspect. It looks smaller in my painting, so it's not accurate. Okay, it's the same width, but it's not so long. It becomes shorter. Okay, so you can see it, it's called ladder paradox or pole in the barn paradox. Okay, and she explains it really nice, better than I will. Okay, so the whole thing is meant to protect from a comet that comes to Earth, like in Armageddon or something. Okay, so in the movie with Bruce Willis, that we found out about a comet and we need to solve the problem, and you know that their solution doesn't necessarily work. It will just create 2 comets that will or a pile of ice that will hit Earth just the same. So so what we are doing is something else. Okay, what are we doing? We excavate from the dark side of the moon a huge piece about 1/4 of the size of the object that is about to hit Earth. If this is not possible, see second and third options below. We lift it from the moon far away from the Earth. In parentheses, on the moon, this giant piece has only 1/6 divided by 6 of the weight as compared to on Earth. Okay, so we have the moon. Okay, let's say this is the moon. And we take away, if this is our comet, okay, which is about to come, we should see it in advance. Then we would take a part that is like 1/4, okay? So it would be in the moon, it would be like in the dark side of the moon. It would be like a tiny piece of the moon, like, let's say like this, okay? And also it weighs only 1/6 of what it would weigh in on Earth, okay? Because the moon is a lot smaller. Okay, so we remove it from the moon and slow it gradually. We move it to a Lagrangian point where it is stored. Okay, if we have, I'm erasing everything. Oh, I will explain what is the Ehrenfest paradox. The Ehrenfest paradox I'm explaining, I didn't find a video that explains the Ehrenfest paradox. So this just gives you a feeling, but you should read in Wikipedia, and especially in Wikipedia in simple English, which is easier. Okay, but in short, Ehrenfest paradox means we have a disk. Okay, this is like a solid disk. And when it rotates, okay, this whole thing rotates, and this is the center of the disk. And if it rotates and the radius doesn't change, then we have the perimeter shortens. Okay, so this is a part of the perimeter. Perimeter shortens. Okay, just like the ladder that we talked about. And because it shortens and the radius stays the same, so this radius here, the inner radius, let's call it, will be even can get bigger than the external radius, because the more you go to the away from the center of the disk, the more quickly you move. Okay, this here moves slower in the same time. Okay, it's like my hand, and my elbow doesn't move almost at all, and my palm moves fast. Okay, so this is fast and this is slow. So this will shorten a little bit, and this will shorten a lot. So the perimeter, the whole perimeter shortens a lot, and this is the paradox, like how come it stays intact? Okay, because it's like how come that the perimeter, which is outside, is smaller than the inside. It's like in Doctor Who. You remember the inside, it's bigger on the inside. Okay, so this is the Ehrenfest paradox. The solution is that in the space-time itself is like, if you look from the side, okay, if this is the disk from the side, then the space-time itself, which we don't see, we cannot see, but it becomes, if this is rotating very fast, it becomes like this. So here the space compensates for this change in the shape of the disk. Okay, so here there is a lot of I don't know how to explain this exactly, but the solution is that the space itself changes. Okay. So okay, so I'm moving on. We remove a piece from the moon, and we move it to the Lagrangian point where it is stored. Okay, we talked about it. It's like a parking place in space. Remember from other inventions. We install on the huge piece rocket engines and drones with lasers. When an asteroid is detected, we drag the huge piece to a collision path with it, so it will defend the Earth before the object can hit the Earth. Okay, so let's draw it. So we took this piece and we put it in the comet did not arrive yet. and we prepared in advance a piece that we think would be in about the size of a deadly comet, and we put it in, we drag it to the Lagrangian point between the moon and the Earth. Okay, so just one thing before I erase this. This is space-time. And the result of this is that in high speeds, the disk itself has like the opposite of the centrifugal force. Okay, in Newtonian mechanics, in slow rotations, it has a centrifugal force that wants to throw everything away. But in very high speeds, when it's a considerable portion of the speed of light, then this has a force because of the gravity that is towards the inside. So here there is a lot of gravity here, and it pulls the perimeter inside. Okay, so it's like it keeps it together. Okay, so Ehrenfest keeps the disk together. Okay, in very high speeds. Okay, so we just need to reach these high speeds, and from there we don't need to hold it, it holds itself together. Okay, so we have the Earth. Okay, this is the Earth, like we have America and all the continents, and we have Earth. And we have our disk, the Ehrenfest disk. Okay, I'm not drawing in scale. Of course, this is very small compared to the Earth. It was very small even compared to the moon. Okay, so this is the Ehrenfest disk, and this is the asteroid. Okay, which is again not in scale. It's bigger than the Ehrenfest disk. Okay, so it's like 4 times bigger. Okay, can you see it? Yeah, and 25 minutes. Okay, so it turns out I cannot explain anything in a short time. So we move this to the Lagrangian point, and when we put engines on this. Okay, so we have engines connected to it. and this start to rotate it. Okay, at the beginning it's very hard, and little by little it becomes easier. Okay, so the rocket engines and the drones will rotate the huge piece, the Ehrenfest disk. Okay, and afterwards we can rotate from the middle, okay? After it's already rotating and our rockets are not fast enough, we can rotate from the slower moving part and give the speed here. Okay, we can connect my rockets look like fish, I don't know why. Okay, so after a while, when it's faster, we can rotate from the middle, and like we said, even if in the middle we rotate slowly, in the perimeter it rotates fast. We care that here it rotates fast in a considerable fraction of the speed of light, like 1/10 of the speed of light, because we rotate fast here, and here it's much faster. Okay, so the rocket engines and the drones will rotate a huge piece. When it's the huge piece, when its external part, rim, is close to the speed of light, to fraction of the speed of light, mass grows up to infinity. Okay, so this, like we said, we have this effect. Of course, we don't reach infinity because we don't reach the speed of light, but we reach very large mass. This way, it can block a much bigger object. Okay, so this is why we use this effect, and also because it pulls it together. Okay, and before it falls apart from the rotations in the low speeds, before we get to the Ehrenfest effect that holds it together, we need to hold it together in some other way. So we can use like a chain mail. Chain mail of the knights in the Middle Ages. So they had this chains that made up the armor. Okay, so if something like a sword comes, okay, this is a sword, then it cannot penetrate the chain, because the chain distributes the pressure, the impact. So in the same way, we can make a chain from carbon nanotubes we don't need a lot of mass, we just need like a sphere, okay, a very thin sphere, but it will act like a chainmail, only instead of protecting something from the outside not to come inside to the body, here it protects the chain, is protecting the inside not to fly apart in the low, in the relatively low speeds, not to fall apart because of centrifugal forces. Okay, after a while, we don't need this. We can use the Ehrenfest effect. Okay, a second option we can liquefy. If we cannot carve from the moon and it's too complicated, we can liquefy the material that we excavate piece by piece and print from it like a 3D printer on a much bigger scale. Okay, so it's like we have a second option. We have like a 3D printer. You know, where we have a nozzle and it moves on a bar like this and a bar like this. So we have a big 3D printer, of course, without the frame. We just have the nozzle, in fact. On a much bigger scale. A material, okay, so we can liquefy the material we excavate from the moon piece by piece and print from it a material which is interweaved. So it's denser, it's more dense. This way we don't need a big it's dense and massive without being big, and continuous. In the 3D printing, we weave it in continuous fashion. Okay, so it's like the material itself is more dense, more compact and interlinked. Okay, so this way we don't need a big and continuous piece. Okay, a third option, if we conclude that the huge piece is not solid enough, we can coat it in a continuous cover like the glazing of a cake. Okay, this is what I described here in more detail. Okay, so this is it. This is my invention, and I hope it was clear. And I'll see you in my next invention. So thank you very much. Goodbye. Thank you.